Welcome everybody who's joining. We're just giving it a couple more minutes to let people join the call. Okay, let's make a start. Thanks everybody for joining. My name is Ian Wiggins. I'm a hearing scientist at the University of Nottingham, and I'm the vice chair of the research board for the HELA research co-op. HELA stands for Healthy Ears Limited Annoyance, and we're going to be launching our first funding call soon, which will make funds available to support research into safe listening in the first round. So how to look after people's hearing in sort of public spaces, at music venues and events in particular. And so in the lead up to that, I thought it might be nice to share a couple of the projects that we're working on in that area here at the University of Nottingham. So the work I'm going to tell you about today is led by my PhD student, Demi Oshin, who's now in her second year here at Nottingham. And alongside myself, she's co-supervised by Professor Graham Naylor, who's also at Nottingham, and Dr. Adam Hill, who's at the University of Derby. So the context for the work that I'm going to talk about today is that we've got reasonably good now at protecting people's hearing in the workplace. So, you know, there are rules and regulations about noise at work that are designed to look after people's hearing in sort of traditionally noisy industries. However, we are still really quite poor at protecting people's hearing in other environments, especially listening to music out and about. And you only have one set of ears, so it's the same ears whether you're at work or at play. And it really only makes sense if you're looking after your hearing in all the environments where they're exposed to potentially hazardous sound levels. That situation is starting to change a bit, and in recent years, the World Health Organization has been very active in this area. And I worked with them a few years ago on launching the global standard for safe listening venues and events. So this aims to set out kind of best practice guidelines for how sound levels should be managed at music venues to help look after the hearing of audiences. And then the HELA initiative has recently launched, and this combines a kind of training certification element and more recently the research cooperative. And this is really gathering a lot of interest now from all around the world. So it's doing a lot to raise awareness and upskill people in these areas. And we're seeing also this having some impact, in industry and out and about. So the Nighttime Industries Association has a Listen for Life campaign. And interestingly enough, Nottingham was recently announced as the first Listen for Life city. So the city and lots of stakeholders locally have made a commitment to looking after people's hearing when they're enjoying Nottingham nightlife. So although there's a lot of really positive things happening from a research perspective, there are quite a lot of things that we still don't know. So lots of questions that need answering. In part, that relates to what's actually safe. A lot of the recommendations that we have come from the noise at work scenario or context. And when we think about sound exposure in music venues, there are some important differences. So music venues, the sound exposure, there's typically a very heavy emphasis on low frequencies that may or may not be present in industrial situations. And generally speaking, it's more likely that you're exposed to very high sound levels, but perhaps for a shorter duration. because most people, unless they work in the industry, aren't spending kind of 40 hours a week in a gig venue. They're spending a few hours, but listening at a very high sound pressure level. So there are differences in the spectrum and also the temporal patterns of exposure. And, you know, to a first degree, we use the equal energy principle to account for those differences. But there's still more that we need to learn about the specific risks involved in music exposure. And also the criteria that we have for what's safe, a lot of that is based on really just making sure that at the end of a working lifetime, people still have functioning hearing. So it's designed to allow a little bit, but not too much audiometric hearing loss. But what we've learned in recent years is that you can do all kinds of profound damage to your ears that doesn't reveal itself in the audiogram. So if we really want to keep people safe, we need to be making sure that we're not causing those kinds of injury, which appear before there's any sort of measurable change in the conventional hearing test. We also need to do more research into what actually works. So how should we monitor sound levels at venues and events? How should we provide that information as feedback to the sound engineer, for example? How should we design sound systems to make safer listening environments? What's most effective in terms of room acoustic treatments? And, you know, what sort of personal hearing protection should we be advocating that people use? And how effective is that? And how effective is it both at protecting people, but also at maintaining sound quality? So there are all sorts of areas where there are still interesting questions to be asked about what works. And then, of course, even once you've established what works, it's another question to say, well, how do you actually change people's behavior en masse? So there is interesting research to be done looking at education campaigns, awareness raising campaigns, how to engage the industry, whether regulation works, whether it should be top down or sort of industry driven approaches. So all sorts of implementation questions where we want to know what's actually effective. And ideally, we have an evidence base to show that. This is quite a challenging area to do research in because it would be unethical, obviously, to bring people into the lab and expose them to dangerous sound levels and then measure what injury we've caused to them. So with that in mind, we sort of need to look opportunistically look for opportunities to conduct this research out and about in the real world, where people are going to venues and events out of personal choice. And so, yes, they're exposing themselves to a hazard, but you know, we're not asking them to do that. We're just sort of observing what happens when they're in that environment. The difficulty with doing research in the real world is that means there are an awful lot of uncontrolled variables. And, you know, there are things you can do to try to control for those things, but it's challenging. And it generally means that you have to sort of go towards large data sets to try and at least statistically average out some of that variability. So I'm going to talk now about a couple of the projects that we're working on currently, which sort of, they're not doing the research directly at the moment, but what they're doing is building tools that will facilitate research in this area so that in future we can do bigger and better research into safe listening. So the first project is, I'm going to introduce you to something called db-SBL. And that is our name for a common data model that's specifically designed for working with sound level data from music venues and events. And the db-SBL in this case is standing for Database for Sound Pressure Levels. One of the reasons that we need this project is that there are many different types of sound level meter. Pictured here are a collection of handheld sound level meters, but there are also other formats of logging sound level meters, and sometimes it's some software built into a laptop. So there's all sorts of different equipment that gets used. And because that equipment comes from different manufacturers, they tend to export the data in their own sort of unique format. So you might well have different ways that time is represented, different columns, different headings, different ways that the same thing is labeled. And that makes it really difficult to combine data from different pieces of equipment or data collected at different times, because you have to somehow make sense of all of this, this variability. And not only that, even if you can sort of get around the technical hurdle of lining everything up and knowing what kind of measurement data you're dealing with, unless you have access to the notes of the person that sort of did these measurements in the first place, you don't necessarily know what it is that they measured. So you could have a sound level meter saying the level is 93.5 decibels, but do you know whether that sound level was measured at the front of house mixing desk? Or perhaps it was measured in the center of the audience. Maybe it was measured on the side of the stage. Or perhaps it was even measured, you know, a few kilometers away at the nearest neighboring site. And depending on which one of those is the case, the meaning of that measurement is going to be completely different. So you can't compare the numbers unless you understand the context in which the measurements were made. So our aims with this common data model, DBSBL, are to make it easier to combine data from different places, times, and measurement systems. And what we also want to do is embed meaningful descriptions alongside the data so that we keep track of, you know, the context in which measurements were made. The hope is that that will increase data longevity and facilitate reuse of data, because an awful lot of this data has been collected by different consultants and researchers, and most of it, you know, doesn't really live on beyond the project where it was first collected. And we would like to change that so that we can reuse this data for research. And we also intend to sort of develop standardized analysis and visualization tools so that wherever your data came from, there's a standard set of tools that you can use to analyze and visualize it. So to design this, we took inspiration from something called OMOP, which is essentially a common data model for healthcare data. And it's designed to sort of solve similar problems, because in healthcare systems, different hospitals and clinics use different databases and different platforms. And then when you want to aggregate all of that data for research, you have to somehow harmonize it so that you can combine data from different sources and work with it on a common platform. So we're doing the same kind of thing, but not for healthcare data, but for sound levels. The sketch is hand-drawn because things kept changing a lot as we iterated on this. But there are two main parts to the DBSBL common data model. The first is a database schema, and that's sort of what's shown here in the diagram. So each of these boxes is a database table in the system. And at the core of the database are sound levels. So these are the measurements, but also some other related aspects. So for example, was there a sound level limit that was enforced when these measurements were made? And also a correction, because sometimes you can't measure where you would like to measure. For example, you can't generally put a sound level meter in the center of the audience because it's not safe to leave it there. So you might measure at the mixing desk, but then you have to correct your measurements so that they reflect the audience area, for example. And then around those sound levels, we've got these other tables that provide that sort of meaningful context. So in the measurement context bracket, we've got information about who made the measurements, what sort of equipment was used to make the measurements, and how and when was it calibrated, and also what particular sound system was in use at the time these measurements were made. Then we've got the spatial context, which includes kind of where was the measurement position? Was it on stage, in the audience, at the mixing desk, for example? But also where in geographical sense, like what venue were these measurements taken at? Then there's the temporal context. So was there a particular event going on at the time the measurements were made? And what were the weather conditions like? Because that can obviously affect sound level measurements. And did anything else happen whilst the measurements were taking place? Was there a power cut or a security alert, or did an alarm go off? anything that might well have affected your sound level measurements. And if you don't capture it, then you can't take that into account later on. And then there's an additional bit called the fact relationship table, and this just kind of glues everything together. So this might encode, for example, that Glastonbury Festival as an event took place at Worthy Farm as the venue. So it sort of ties the different records together. And then the second part of the common data model, which is really important, is having a standardized vocabulary. So everything that gets stored within the data model, the idea is that it uses these standard terms so that everybody is using the same term to describe the same thing. And that's what allows you then to use standardized analysis and visualization algorithms. So when I talk about standardized vocabulary, essentially what that is a hierarchical tree of kind of well-defined concepts. And wherever possible, we don't want to reinvent the wheel. So if we're talking about different types of sound levels, for example, we'll take the relevant concepts from well-known published standards. So the standards that describe sound level meters, for instance. So just to give you an example of how the standard vocabulary works, say we'd made some sound level measurements using the A weighting, frequency weighting curve, and we wanted to encode that in the data set. So we would go across the first column here are what we call the domains. So we would go to the sound level domain, and then we would go to the frequency weighting concepts. And within there, we would find an A weighting concept. So we would use that to denote that these measurements were A weighted. Similarly, just as another example, if we wanted to say that the measurements were made on the stage, we could go to the measurement position domain and then go to measurement position type. And in there, we have a concept describing on stage. So we've sort of implemented the data model now, and we've built up a standardized vocabulary. And what we're doing now is validating that works. And so we needed a data set to work with, and the one that we're using for now comes from a case study that my colleague Adam Hill and I conducted at the Serendipity Arts Festival back in India in 2023. This was a WHO-sponsored case study where the festival was aiming to become the first sort of large-scale event to comply with the WHO global standard, which it pretty much successfully did. But for our purposes now, we have this quite rich data set because we collected data across the full 10 days of the festival, and we were monitoring at 8 different venues across the city. And at most of those venues, we had sound levels in at least 2 locations, typically at the front of house mixing desk, but also on stage. So we've got a really rich data set with a lot of data, a lot of different types of measurement position, and a lot of metadata about what was going on at the time because we were on site recording that stuff. So we figure if the common data model can handle this data set well, then that's a good indication that it's sort of fit for purpose. So that's where we are now, and once we've done that, we're not quite there yet, but soon we'll be releasing the common data model because it's useful to us for our research, but the idea is that it's a community resource that other people can use and that can facilitate sharing of this kind of data in future. So the intention is to release this open source on GitHub, which will include the database setup files, the standardized vocabulary, and also all of the kind of scripts that go along with it for loading data from your sound level meter into the common data model, and then producing standardized charts and analysis. So yeah, that's coming soon. And we're going to go on to talk about a second project now, but I'm happy to pause if anybody has any questions about that project before I move on. Feel free to raise a hand, or you're also welcome to post questions in the chat, or we can also do questions at the end of the webinar. Okay, so no questions immediately, so I'm going to go on and talk about the second project that we're currently working on. So this is about using smartphone-based location tracking to monitor personal sound exposure. And to give you an idea of the problem that we're trying to solve, it's obviously a really good thing to be able to measure sound levels at venues and events and do that accurately and record that information and store it for future use. But if we want to understand the impact that the sound exposure has on individuals, then we need to know what that person's personal sound exposure was. And how much exposure an individual gets varies a lot. And one of the ways it varies is sort of how long that person spends at the venue or event. So you have to know when they arrived and when they left. Because clearly, at a festival, for example, if you are there for one day, you're getting a very different cumulative sound dose to if you were there for a week. And another thing that really matters is where somebody actually spends their time whilst they're at the venue. So typically, there's often going to be quite a significant gradient of sound levels from the front of a venue to the back. So an individual is going to get a very different sound dose if they are planted right next to the loudspeakers near the stage compared to if they spend most of their time at the back of the venue. And along similar lines, a lot of venues will have multiple rooms. So there might be a main space, but then there might be a bar and a separate room where sound levels are lower. There might be a chill out room. So where somebody spends their time is as important as how long they're there, because all of those things together really affect what a person's personal sound exposure is. So the traditional way to measure kind of individual sound exposure would have been to give somebody a personal dosimeter, which is a miniature sound level meter that you wear on your body. And it sort of tracks your cumulative exposure over a period of time. And have been a few research studies, for example, at festivals where the researchers gave volunteers these personal dosimeters and sent them out to enjoy the festival. And, you get good data that way, but clearly there's the logistics and the expense of providing these devices. And then people have to use them and they have to look after them. And at a festival type environment, it's really tricky with weather, and as people add extra layers in the evening and they cover up the microphone, and so it's pretty tricky. So the solution that we're looking at working towards is, well, can we make use of something that people already have on them? And nowadays nearly all of us are carrying a smartphone most of the time. So we want to know if we can track somebody's movements at and throughout a venue or an event using their smartphone. And the way we're doing that, there's a few different ways that you can track the location of a smartphone, but we've decided that for now we think a Bluetooth-based method is the most suitable here. So we've bought some of these Bluetooth beacons. They're small, just a few centimeters in size, and they emit sort of constant Bluetooth, or not constant, but they regularly emit Bluetooth signals, which span out from the beacon and are detected by the Bluetooth receiver in a smartphone. And so the assumption we're making is that sort of where the individual goes, their smartphone goes with them. So if we can track where the smartphone goes, hopefully we can track where the person that owns the smartphone has been. And this is going to get better with future releases of Bluetooth, because the newer Bluetooth standards have sort of fancier ways of tracking location. But for now, we're working with a sort of more basic approach, which is to use the strength of the signal that's received. So the phone, when it receives a Bluetooth packet, it will give you something called the Received Signal Strength Indicator, or RSSI. And this is basically a measure of how strong it thinks the signal was that it received from that Bluetooth beacon. And essentially, as you might expect, the strength of the Bluetooth signal falls off with increasing distance from the beacon. So as you move further and further away, the RSSI value decreases, and you can fit a smooth curve through that relationship between RSSI and distance. And so from the RSSI, you can kind of work backwards and estimate how far away the smartphone was from that particular beacon. So this is called a range finding approach. And then you use an approach that's sort of similar to what happens in a GPS system. So using trilateration, for example, if you have estimated that you're 4 meters away from a first beacon, then you know that your position is somewhere on a sphere of radius 4 meters surrounding that beacon. And then maybe you have a second beacon that you think you're 6 meters away from. So there's a 6 meter radius sphere surrounding the second beacon. And as long as you've got at least 3 beacons, but ideally more within range, then you know that the point where your receiver is where all of those spheres intersect. So that way you can sort of use the distances to estimate the location of the smartphone. So we've been putting that to the test recently, and Demi developed an app. So the app runs on the phone. We have these beacons set up around the room. The smartphone app receives the Bluetooth signals and measures the signal strength, and then it immediately uploads that to a server on the cloud so that data is available for analysis. And we're testing this out in the rehearsal hall at the music department here at the university. And here are some initial results that we got. So this is a sort of floor plan of the space. And the measurement locations, the correct measurement locations is shown by the red crosses. And then the blue circles are where we estimated the smartphone to be using this Bluetooth tracking method. And we were reasonably pleased with this. It sort of seems that we get in the right ballpark. That said, there is typically an error that's, of the order of up to 4 or 5 meters between the correct location and where we estimate the location to be. And this is kind of best case as well, because this is standing still with the smartphone for 30 seconds, getting a good amount of data to average and nothing moving around. And if we tried to track a moving target, we found that the performance was worse still. So we've been looking into why is that happening and what can we do to improve the accuracy of this system. And one of the things we've realized is that, unfortunately, we sort of naively assumed at first that these beacons would have an omnidirectional radiation pattern, but that is not the case. So here's some measurements we made in situ in the rehearsal hall. And you can see as you go off towards 90 degrees on either side, so towards the sides of the beacon, there's a very strong drop off in the amount of signal that's radiated in those directions. But interestingly, there's also quite a significant asymmetry even in the more central region, so sort of directly in front of the beacon. If you look, for example, at the difference between minus 30 degrees and plus 30 degrees, so this is just, a bit to the left or a bit to the right, there's a difference in the radiation strength of around 7 decibels or so. And that's quite significant, really. In the free field, the received signal strength is dropping by 6 decibels every time you double your distance from the beacon. So what this means is that you could be on one side of the beacon and think you were 4 meters away from it. If you were a bit on the other side of the beacon, you would think you were 10 meters away from it, even though you're actually the same distance away from it. So we've realized that we really need to account for the specific radiation pattern of the beacon if we're going to get these systems to work accurately. And the other thing that we realized pretty quickly is that the free field model for path loss between the beacon and the receiver just doesn't work very well when you're in an indoor environment with a lot of reflections. So the situation is a bit like acoustic reverberation. You've got a lot of signals bouncing around within the enclosed space, and all those signals reflections interact to determine the actual signal strength that you're going to measure on the smartphone. So what we're doing now is using a sort of ray tracing model to look at the multipath propagation between the beacons and the receiver to get a more accurate estimate of the received signal strength. So this is work in progress, but what we're doing at the moment is to correct for those things. With the RF lab at the university has kindly lent us a bit of time in their anechoic chamber. So this is one of our beacons installed on a measurement turntable in front of a reference antenna. And so we're measuring the polar pattern of the beacon with much greater precision. And then that trilateration algorithm that I described earlier, it turns out that only really works if you've got pretty high confidence in your estimates of distance to each beacon. And if you get the distance estimate wrong, then the trilateration algorithm kind of falls apart in a not very graceful way and gives you quite unrealistic predictions of where the receiver was. So we think we've got a better way of doing it now, which is essentially we set up a sort of dense grid of receiver positions throughout the venue. And then we use ray tracing simulations to say what would the received signal strength be from each beacon at every possible receiver position. And then rather than using the trilateration approach, we're actually now training a deep neural network that takes the signal strength from each beacon as its input. And then it has some hidden layers that combine those values in a way that hopefully increases its robustness to measurement error. And then the output from the network gives us the X, Y, and Z coordinates of the smartphone. And we're finding this to be a much more powerful and robust approach, which we think holds a lot of promise for more accurately tracking the smartphone through the venue. So some of the pressing questions that we are looking to ask ourselves in the coming weeks. We want to know, with this improved process, how accurately can we track the location of the smartphone? And then once we know that, how does that translate to sort of the uncertainty with which we can quantify somebody's personal sound exposure? So if we know the distribution of sound levels throughout the space and we know where the smartphone went, then we can calculate the sound exposure. We want to compare that to dosimeter measurements to make sure that we're getting that accurate. And then crucially, we need to see, does this solution hold up in real world environments? Because it's one thing to do it in an empty room with one smartphone moving around. But obviously in a real music venue, you might have hundreds or thousands of people, each with their smartphones, lots of movement, lots of obstruction of the signal paths, and everything's very dynamic. So it's going to be really interesting to see how well this can work in those more challenging real world environments. So I'm going to carry on. I'm going to describe what we're hoping to do next with this research. And the idea really is to combine the two projects that I've just talked about. We want to link all of this up. So we've got accurate measurements of sound levels in venues. And then using the smartphone-based location tracking, we hope to be able to get accurate, personalized estimates of sound exposure. And then we want to know, well, what's the impact of that sound exposure? So what's the audience members' experience as a result of being exposed in that way? And we want to know both about the satisfaction of the audience members. So we want to ask people, what kind of sound levels do you prefer? What objectively makes for a good experience in these music venues? But also the impact on people's hearing health. So are they experiencing any short-term symptoms after that exposure? For example, do they have any acute tinnitus or a dulled sense of hearing or any ear pain, anything of that nature? And what we want to do is use a kind of citizen science approach to mean that we can do this sort of research on a much greater scale than has been possible in the past. So here's just a sort of illustrative example of how we see this working. So imagine a city like Nottingham, but it could be any city. You've got music venues of different sizes and hosting different types of events, from nightclubs to gig venues to sort of multi-use arenas, outdoor sites. And so we want to have sort of logging sound level meters set up in different venues around the city so that we're continuously monitoring the sound levels in different spaces. And then we can have volunteers that have this app on their smartphone. And because of the geolocation abilities of the smartphone, we can know when people visited these venues and events, and we know the sound levels in the physical space. We can tell from the smartphone, when did somebody arrive, when did they leave, so how long were they at that venue. More than that, we can sort of track them within the venue and say, well, how much time did they spend in the main space, how much time were they in the bar, and from that estimate their personal sound exposure. And then what we want to do is sort of send targeted questionnaires through the app to ask people their follow-up symptoms and attitudes and experiences of the sound environment in these different venues. So that's how we can see it working on a city level. But again, all of this we plan to release on GitHub as open source tools and platforms, so that people can do this not just in Nottingham, but in other cities and indeed around the world. And we think that with those tools, we can sort of open up a level of research in this area that just hasn't been possible in the past, and really target much larger data sets and get better insights into what makes for safe but also enjoyable listening experiences in music venues. So thanks very much for joining the webinar, and thank you for listening. And if anybody has any questions, please feel free to either come onto the call and ask them directly, or you can post them in the chat. Thank you. Go ahead, Dave. Sarah, are other people able to unmute themselves should they wish?
Yes, you can now do that, David.
Great, thank you.
Okay, hi.
Hi, Dave.
Hi, Ian. Sorry, I got a bit lost with the space then. Very nice presentation, very clear. And I'm absolutely delighted you're working in this area. It's one where we need a bit of solid rationale. So just to take up your second issue there about this using smartphones, I may have missed something, but are you actually thinking about using smartphones to measure loudness levels or volume levels at the point of the individual as well?
Yeah, good question. I didn't really address that. We are thinking about it, certainly. And I think what we want to do is compare that approach to the alternative. So the approach that we're proposing at the moment is not to use the smartphone microphone as a sound level meter, but rather to separately measure the sound levels in the environment and then track the movement of the person via their smartphone through that space, and then sort of post hoc estimate what the sound exposure would have been. Definitely there's something to be said for trying to use the microphone in the sound level meter, but people have looked at that previously, and as you probably know, depending on the manufacturer of the smartphone, the accuracy of the microphones and the tolerance is greater or lesser. And then you've got the issues of, is the smartphone in somebody's pocket or in their bag, and where's the microphone pointing? So I don't know, my instinct is that it's going to be hard to feel a lot of trust and confidence in the readings that we would get from smartphones acting as sound level meters. But I think it'd be really interesting to compare the two approaches and see how valid those measurements are. And the other thing is, of course, you can crowdsource that data. So you have maybe 100 bad estimates of the sound level from different people at the same venue. And maybe if you average 100 bad estimates, you get towards one decent estimate. But we will see. But yeah, good question.
Yeah. So just taking a sort of a lateral look at the general question of leisure noise, you might remember that way back, Michael Aykroyd and others at IHR and I were involved with a centennial study in which we were looking at the involvement of music, listening levels on hearing, and what we came up with in that, which has never been published, I'm embarrassed to say. There is a paper floating around somewhere, but hopefully it'll get there. But what we found was essentially that there was very little indication in our sample of over 4,000 people of leisure-related music exposure and hearing level as measured by the digits in noise test. So, you know, I'm a bit skeptical of the WHO approach of using working at noise, and in fact, during the time that we were looking at the UK Biobank data, we found that there was a definite relationship with work noise, but not with leisure noise. Sorry, I've got a cold here at the moment. I might stop there.
So, sorry to hear it, Dave. I'm just getting over one here. Sounds like you're still in the midst of it. Yeah, no, I think you're right. I think that speaks to why we need good quality research in this area. It's so hard to quantify the exposure in the leisure noise setting. And what else can I say about that? Yeah, I mean, clearly audiometric loss is not the full story, as we know now. That there are other types of loss that precede audiometric loss, although fair enough, you were talking about speech and noise tests there. But I know Sarah Verhulst, for instance, has recently been doing some work in this area, looking at post-festival attendance and using sort of a battery of measures with greater sensitivity to subclinical hearing loss, and finding that there might be effects there. I mean, there's no doubt that the sound levels in these environments are hazardous. You know, if you're there long enough, it can be extremely high SPL. And we know that that can cause damage, but the question of how much and how the pattern of exposure is important. I think we still have a lot to learn. Okay, thanks, Dave. Does anybody else have any questions? If not, then you can always message afterwards if anything comes to mind. And please keep an eye out for the funding call if you're interested in doing any research of your own in this area. And otherwise, thanks all for joining and hope to see you soon.
Hey, Ian, can you email me?
Yes.
Because there's a UK Biobank thing coming up in which we'd be interested in your input.
Oh, sure. I'll drop you a line.